Alright, let's go ahead and go over our second problem. Okay, so consider this equation. So part A seems to be a boundary problem where we're given the initial condition, so probably we can find the value of C. Okay, so part A, you can go ahead and find the integrating factor, which is going to be e to the power of the integral of cosine x dx. So this is going to be sine of x, e to the power of sine x. So let me multiply this to both sides of our equation. 1 plus cosine x y is going to equal to e sine x times e negative sine x. Alright, so next part is we're going to take the integral of both sides. And please note that we have the same base, so we get to keep the base, and we can add the exponents. So sine x plus negative sine x, that's just going to be 0, which is 1. Alright, so keeping that in mind, our left-hand side is e to the power of sine x times y. That equals 2. The integral of 1 is just x. And we have our constant value. We can divide both sides by e to the power of sine x to get the y by itself. And usually this would be our answer, but in this case we can plug in x for pi for x, to find the value of c. So let's do that. That is going to be pi over e to the power of sine pi plus c over e to the power of sine pi. We know that sine pi is 0, so this is pi over e to the 0 plus c e to the 0. E to the power of 0 is 1, so we know that pi plus c. We know that this should equal to pi. So we know our c value should be 0 in this case. So to answer this question, our final answer is phi of x equals 2. C is 0, which means 0 divided by whatever. It's just going to be 0. So it's just going to be this part, which is x over e to the power of sine x. Okay. Let's go to part B. Alright, so part B is different from part A. So we can just simply use our general equation, and we have to prove that this is the case, where k is any integer. Okay, so if I go back, our general equation, I'm going to start from here, which was y, or you can write phi of x equals to x e to the power of negative sine x plus c over e to the power of negative sine x. I think that's what we had. Yeah. Oh, sorry, without the negatives. Alright. So that's what we had as for our general case. Let's plug in pi, k, and 0 respectively, and then we can subtract those things. Okay. So phi of pi k minus phi of 0, this is going to be pi k over e to the power of sine pi k plus c over e to the power of sine pi k minus 0. So 0 over e to the power of sine 0 plus c over e to the power of sine 0. So sine is a graph that is periodic and continuous. It just goes like this forever. And all of these values, this is pi, 2 pi, and probably 3 pi, all of these values, sine is going to take on zeros. So we know these are going to be e to the power of 0, likewise e to the power of 0. Same thing, sine of 0 is 0, so e to the power of 0. And anything to the power of 0 except 0 itself is going to be 1. So we can rewrite this and say pi k plus c minus 0 plus c. This can be rewritten as pi k plus c minus c, so c's cancel out, and we get to pi k, which is what we wanted, so we're done. Let's go on to problem 3. Okay, so this given equation is not necessarily in our general format, so let's go ahead and divide both sides by x squared. So we have y prime plus 2y over x equals to 1 over x squared. Okay, so let's find the integration factor of x. So this is going to be e to the power of the integral of 2 over x dx. That's going to be 2 ln of x, but we know that from this given, x is always going to be a positive value. So we can just get rid of the absolute value sign and do e to the power of 2 times ln of x. We can rewrite this as e to the power of ln squared. By doing this, we just get to x squared. Okay, so I can multiply x squared to the both sides of our equation. X squared. Sorry, I should probably use this equation that we have. So we have y prime plus 2y over x, that's going to equal 2. X squared times 1 over x squared is just 1. Integrate both sides dx, and we have x squared times y, that's going to equal 2 x plus c. Okay, finally, to get the y by itself, we can divide both sides by x squared, so we can rewrite our final answer as v of x equals to 1 over x plus c over x squared. Part A asks, show that every solution tends to 0 as x goes on to the infinity value. So probably from calculus 2, we know that if we use the limit, apply limit of x approaching infinity, this value is going to approach 0. Likewise, this value is going to approach 0. Alright, so 0 plus 0 would end up to 0, which proves we have shown that every solution tends to 0 as x gets bigger and bigger. Alright, and let's go ahead and do part B. So part B, we can use the answer that we got for part A and plug in these values, 2 for x, and hopefully we can prove that that's going to be equivalent to 2 times the phi when x is 1. Alright, so let me find the phi of 2 first. So that's going to give us 1 over 2 plus c over 4. Let's find 2 times phi of 1. So that's going to give us 1 plus c over 1, which is just 1. Alright, now we have to set these two things equal to each other. So we have 1/2 plus c over 4 equals 2. 2 plus 2c. Let me multiply both sides by 4. So we have 2 plus c equals 2. 8 plus 8c. That gives us 7c equals 2, -6, which finally gives us c value as -6 over 7. Alright, so our answer for B would be phi of x would be 1 over x plus negative, not plus, negative 6 over 7 times x squared. Alright, so last problem, which number 7, I was hoping that you guys can get at least some things started using, utilizing the concepts in linear algebra. So this probably is not going to be on our exam ever, but this was more in hopes that you guys can reflect back on the concepts that was talked about in linear algebra. So I'll give a brief overview. So we have first observed that we can utilize the equation given in our textbook. So I think this was equation 7.3, that the solution for this general case was, well, the integrative factor we know is going to be always a of x dx, and our phi of x equals to e of negative a of x times b of x plus the constant e to the power of a x. And in our textbook, the capital A of x is the integral of a of t dt, some kind of t value, and also b of t was also e to the power of a t d times b t of dt. And these were given as we were trying to prove, or as these were given in our textbook with some brief proof. So we first observed that the matrix of the exponent of, I guess our periodic period is eta, negative eta, a of x minus I is our identity matrix. We first noticed that this is invertible. Okay, so if 1 is an eigenvalue of the matrix of, let's just take this one, if 1 is an eigenvalue of this set, then 1 is an eigenvalue of the matrix likewise of the e to the power of negative k eta is this, times a of x. K is K is going to be at all integers, any integers. But we notice that this is impossible since as this value approaches to 0, this value will approach to 0 as k value, or any integer, will approach to infinity. So consequently, we get that this value, just the first part, is invertible. So of course, everything, including our identity matrix, this whole thing is going to be invertible. So now we defined the transpose of this as the e to the power of t times a of t. T is some kind of constant value, not constant, continuous value, and this is going to be multiplied to the initial value of the x, the transposed x value, plus this is going to be the e to the power of negative s times a of s, f of s times ds. So again, this concept comes from the probably the linear algebra, and the only solution that we can have for this, the transpose, is the phi has to be the periodic. And if this, we just proved, first we proved this part that exists, and we know for the periodic function that these two are going to be equal. So